Well, first, I have a conceptual question.
Okay.
When you were talking about the reflective properties of ellipses,
Uh-huh.
does is it similar to, or do parabolas have
Yes,
their own reflective properties?
they do. Here, if I draw a parabola, just draw the most basic one. Y equal x squared. Okay. It's got a focus somewhere right there. If you send a tennis ball, it will always bounce to the focus. As long as you send it in parallel to the major transverse axis, or the axis of symmetry. If you send in a tennis ball and it hits up here, it still bounces to the focus. You send it in down here, or a ray of light from a star, everything bounces to the focus. So if you are building a telescope, you shape it like a parabola. You take a parabola and you spin it about the y-axis and you create a three-dimensional paraboloid. And that paraboloid has these reflective properties.
Okay.
Okay? And the thing you're probably more used to is a light bulb or a flashlight. If you have a flashlight, you make the outside of it look like this. And then you put your bulb right there. And it works both ways. If I send a ray out from the bulb, it always goes out vertically, no matter where it hits on that paraboloid. And what that does is focus the light. So you get a light beam from your flashlight rather than just a bunch of light that gets dispersed and goes in all different directions.
Right.
So the reflective properties of a paraboloid are as important as the reflective properties of an ellipse. If I have an ellipse that has two foci there, then wherever I shoot a light ray or anything else, it'll reflect to the other focus. No matter where, right? In other words, if I fire it there, it comes back to that right there.
Right.
And this is used for if you have like a gallstone and they want to shoot it with sound waves to break it up, or a kidney stone or something, then they'll place you in a device that is not a full ellipse, but maybe it's a half of an ellipse. In other words, maybe it is this much of the ellipse. Oops, I didn't draw that quite right. But assuming that that was the focus, so they'll put their sound machine and they'll put your body with your gallbladder right there in a chair. And then all of the rays from that emitter of sound, every one of them, wherever they bounce, they focus on your gallstone to break it up. Okay? So
Okay.
that's a nice property to have. Um, and in fact, there's quite a few instruments that use parabolas, ellipses, and hyperbolas all in the same instrument. They capture all of the light coming in from the sky, say, with a parabola, and then they take all of the signals that are sent to the focus of the parabola and send that in an elliptical shape so that it goes to another receiver. I can't remember how you would incorporate a hyperbola into that, but they've got, most telescopes have at least a parabola and an ellipse involved.
Hmm. Okay.
and I've had it explained to me how you would build something where you would use all three to get it to your eye. In other words, when you look into a telescope, you're not looking at the star, right? You're looking down. So
Right.
all of the light that is coming in from the stars is going into the lead lens of the telescope, and then it's getting bent and shaped and reflected to your eyeball. And you do that using combinations of parabolas and ellipses and hyperbolas, although for the life of me I can't remember the reflective properties of a hyperbola, but I don't know that you've ever presented a problem that needed them. I can't quite picture how this would work. If I fired something from that, no, if it hit that, it would go that way. I'm going to have to review hyperbolas to see the reflective properties of hyperbolas.
Okay.
All right, what else do you got?
Um, so
Oh, it sounds
what
amazingly good. Did you do anything different? You put a different microphone or anything?
no, nothing different.
Wow, no static at all.
Yeah, it's really clear.
Yeah, okay.
What is the total value after 7 years of an initial investment of $2,250 that earns an interest rate of 6% compounded monthly?
All right. There's three formulas that you have to know for growth and decay. Actually, decay is always just continuous. So nothing decays on an annual basis. Annual compounding is an invention of mankind. The only reason
Right.
we have it is because somebody opened a bank and decided to offer somebody annual compounding, or in some cases, monthly compounding. But most compounding is continuous compounding. Okay? Well, let's talk
Okay.
about annual. What's the formula for annual compounding?
Um,
This would be
A.
annual, this is greater than annual, and this is continual. So in the annual, it's A equals what?
P
Your starting amount.
times 1 plus the rate divided by the time.
Well, actually, the time is the exponent.
Right. The rate
Not
divided.
divide
Oh, the
the
rate.
rate by anything. You divide it by 100 to turn it into a decimal. In other words, you don't want to put in 6%, but 6% is 0.06.
Right.
Okay? So that's annual. More often than annual gets a little more complicated. What is this?
1 plus R over N to the power of N times T.
With N being,
The number of times per year.
okay, cool. And then the third one for continuous is per.
P. Yeah, P.
And the R goes in the exponent.
Right.
Okay? This is greater than annual. In fact, monthly N is 12. So let's set this up. The amount after 7 years is going to be what? Based on the specifics they gave us.
2,250 times 1 plus 0.06 over 12 to the power of 12 times 7.
Correct. And T is in years because your rate was in years.
Right.
If your rate would have been months, in other words, suppose they told you that you got 0.5% a month on your money. Well, I would go ahead and put that a 0.5%, but now my t is going to be in months, not years. So your t is always in the same unit as your rate. And now your calculator will give you that answer.
Okay.
Go ahead and get it, just because I have a good idea. 7 years, 6%, that usually doubles the money. Your final A should be in the neighborhood of $4,000 to $5,000.
It's 3,420.83.
3,400?
Yeah.
Okay.
3,420.83.
Let me just put that into Wolfram Alpha, because I had always heard my whole life that if you could get 6% on your money, you double it every 7 years. So I'm surprised this doesn't come out to be closer to double. Let's see. What was my formula? My formula was 2250 times 1 plus 0.06 divided by 12, parentheses, raised to the 84 power, 12 times 7.
Yes.
Yeah, I got the same thing you got. Okay, well, that must have been wrong what I've been told my whole life. Yeah, I got 3420.83 also. You're good with your calculator. You never make a mistake there doing that, I've noticed. Even when it seems like it's not in the ballpark of where I expect it, well, that's not much of a return for 7 years. Make about 50% on your money is all. Huh. Well, what else you got?
A single cell amoeba doubles every 3 days. How long would it take one amoeba to produce a population of about 10,000?
Okay. So when we're dealing with amoebas and bacteria and population, it's always continuous growth. In other words, any natural thing in nature is continuous. I don't know of anything in nature that compounds annually or even monthly. It all compounds. If it compounds based on how much material is there, it's continuous. So we're dealing with this. They said a single cell doubles how often?
Every 3 days.
Okay. So if I substitute 3 for t, and over here on the left I'm going to put 2p, can I not write this? You see what I did?
3 days.
Doubles every 3 days?
Yes.
But the doubling is expressed by the p becoming 2p.
Right.
And the beauty of that is the p's then cancel and go away. And you're left with an equation that only has one variable, r. And that's the first step of this problem, is to figure out what r is. In other words, now
Right.
I have 2 equals e to the 3r. Take the natural log of both sides, and you end up with 3r equals natural log of 2, which means r equals natural log of 2 divided by 3. So that's r. So now we have a specific equation for amoebas. Not the same equation for bacteria or rabbit populations, but for this amoeba, we know what r is.
Right.
e to the natural log of 2 divided by 3 times t. There is what would be called the specific equation for this amoeba. In other words, stuff that has exponential growth, what was I going to say? Oh, depending on what it is, it's going to have different R's. In other words, a bacteria culture would have an R that wouldn't be the same as this. Population of humans would not have an R the same as this. Anything that grows continuously, which is basically everything except artificial bank accounts and stuff like that.
Right.
Bank accounts of humans invented. Well, once you get R, now you can answer any question they might ask. In other words, if they say, well, how long would it take 10 amoebas to become 2,500, then I would put 2,500 there, I would put 10 there, and I would solve for t. And that would tell me in days. T is in days, remember, because R was figured out based on 3 days it doubled.
Right.
T stays in days. T stays in the time frame that you used to calculate R. And then fill in any t you want, or I'm sorry, you would solve this for t, and that would tell you how long it took 10 amoebas to become 2,500 amoebas.
Right.
You'd solve it like we always do. First step's to divide by 10. Next step is to take the natural log. All of that. All right. What else, William?
The half-life of a substance is found to be 1,000 years. The substance decays by the law of exponential decay.
Okay.
If 1,000 grams are present initially, how many grams will be present in 410 years?
General equation is what?
PE to the RT.
A equals PE to the RT. Okay. I may have actually, there's one thing that's kind of puzzled me on this. I'm not sure why, but it's actually minus KT. When you're dealing with decay, they put a negative sign in front of the K. And like I said, I'm not quite sure why, because you would think that we'll just leave the negative sign out and decay will come back as a negative, right? Should come back with a negative K.
Have a negative rate.
Right, you would think. And that's the way we did a problem once before, and gosh, can't believe it's any different, because we came back with a positive K, and of course then when you put the negative sign in front of it, it's right. But most of the textbooks will list this. Does yours not list it this way? With the negative sign in front of the K, and they don't use R, they usually use K.
I think it does list it as that.
Yeah. All right. It doesn't really matter. I'm still curious mathematically why they insist upon putting a negative sign there as opposed to just letting K be negative. In other words, if I didn't have a negative sign there, when I calculated K, it would end up being negative. How can I use this information right here? That, first of all, in fact, I'm not even going to use the bottom, the middle piece of information. All I need is that information right there. That's going to allow me to figure out K. That tells me the half-life is 1,000 years. So what can I do?
Um,
I
two,
don't really need the starting amount to figure out K. I'm going to need
no,
the starting amount to answer this question.
right.
I don't need it to answer K. What does P become?
2p.
Half-life. Half-life means it's cut in half. It's decay. So it's not
Right.
P, it's 1/2 P.
Well, couldn't you make the p on the other side 2p?
No, you don't want to do that. It makes it so you're not, in other words, conceptually, we're turning P into half P.
Right.
If I put 1,000 in there, in other words, if I used all the information they gave us, then it's 1,000 becomes 500, right?
Right.
It would be this. It would be, I'm saying that 1,000 becomes 500 e to the minus k 1,000 years. That's how long it takes for this substance to go by half. Well, notice that I end up dividing both sides by 1,000 and I end up with 1/2 on the left side, correct?
Right.
Well, if I do it this way, I still end up with 1/2 on the left side, and I don't have to know the starting amount. My very first step, I'm just going to divide both sides by P. With me?
Right.
Okay. And now I have 1/2 equals E to the minus 1,000K. Next step,
Take the natural log of both sides. And you get natural log of 1/2 equals negative 1,000k.
right, so now if I divide by negative 1,000, that'll be K, right? Correct, this?
Correct.
And notice that K is positive, is a positive number. In other words, whenever you take logs of numbers between 0 and 1, you get negative answers. So I got a negative numerator and negative denominator. K is going to come out positive. But that's okay because I got a negative sign in front of it here. I just don't get why they include the negative sign in the general equation. Would we have to? In other words, if when I did it the very first time, I think I did it like that. And if you do the math here, you end up with a negative K. You end up with the same amount, same value, it's just a negative sign with it. So it seems to me that would be sufficient, but there must be something I'm not seeing as to why they need to put that negative sign into the general equation. All right. Now, the rest of the problem I can do. The amount, they're saying, if I started with 1,000 grams, e to the minus that, well, I got to be careful with how to write it here. These are always terrifically hard to write so that they can be read. And 410 years is what t is. Well,
Right.
everything you see on the right side of the equation is a number. So that's going to tell you exactly how much your 1,000 grams decays to after 410 years. Probably it's not down to half because we know it takes 1,000 years to become 500.
Right.
So in 410 years, it's going to lose maybe 20%. I'm guessing it would end up being somewhere around 800 grams.
Yeah. 752.
Okay. It's always nice to know those ballpark because then when you get your answer, you can say, well, I'm in the ballpark. I'm not off by a factor of 10. I'm not more than 1,000. I didn't come up with 1,200. In other words, ballpark is huge to me. It's a huge factor of math, is
Right.
making sure don't have the wrong sign or you're not off by a factor of 10. And you do that by knowing what the approximate ballpark would be. All right. What else?
Let f of x equal x squared plus 1. And find the average rate of change between find the average rate of change of f between 2 and 5.
Okay. Average rate of change means what?
Basically the slope.
Rise over run, right?
Right.
Okay, well, if I graph this function, the perfect parabola shifted up by 1. If I want the average rate of change between the points 2 and 5, then the way I'm going to get it, if this is f of x, is I'm going to figure out the slope of this line. How do I get
Right.
that? I get it by f of my higher point minus f of my lower point, that's the rise, divided by my lower, divided by the run. In other words, this is the rise, this is the run. Okay? So this
Right.
is always what you're going to be using when they ask for average rate of change. Now, what's f of b? F of b is 5. In other words, this is b, this is a, my 2 points. They could be anything, and I could still use this formula. They could have said from 3 to 6, and I just take f of 6 minus f of 3, all divided by 6 minus 3. So here, I'm going to take f of 5 minus f of 2, and divide it by 5 minus 2. So what's f of 5?
26.
What's f of 2?
5.
So I've got 26 minus 5 divided by 3, or 21 divided by 3, or 7. So the average rate of change is 7. If there is a distance between this number and that number of any amount at all, then you're talking average rate of change. In real life, we frequently want to talk about instantaneous rate of change. Well, the only way to figure out the instantaneous rate of change is if, at a single value, is by figuring out the slope of that tangent line. And
Right.
that is the first derivative, first step of calculus, and I hate Windows 10 with a passion. The first thing you learn in calculus, once they get you through limits, is how to find an instantaneous rate of change. And you basically use the same kind of math that you use to find average rate of change, only it's a limit process. You basically are finding the slope of that tangent or that secant line, which represented the average rate of change, as this distance between 2 and 5 approaches 0. If you take the distance between your 2 points and let it approach 0, you end up with the slope of the tangent line and the instantaneous rate of change.
Okay.
When you're going down the highway in your car and you're looking at your speedometer, you're looking at an instantaneous rate of change. At a
Right.
given moment in time, you're going 60 miles an hour. 3 seconds later, you might be going 40 miles an hour. But the instantaneous rate of change is precisely that. It's at one moment only. And you can see why it would be tough to figure out instantaneous rate of change, right? In other
Right.
words, if that h goes to 0, and that becomes a single point, so I basically end up with 0 divided by 0. And who knows what that is? That's why they have to teach you limits to start with. Is because not all 0 over zeros are the same. First of all, it's not 0 and it's not infinity. It can be anything. It can be a number. It can be 0. It can be infinity. Depends on what's constituting the 0 over 0. But that's the difference between average and instantaneous rate of change. And that's why I write it like that. It's because that's the precursor to calculus. You're going to see that a lot when you take calculus.
Okay.
Okay? Only it won't look quite like that. It'll look like this. F of x plus h minus f of x all over h. And I'm going to take the limit of that as h goes to 0. That is the definition of first derivative.
Okay.
What else? I don't want to
With that,
get ahead of yourself, but we shouldn't really be talking about calculus when you're preparing to take a semester final in pre-calc.
no, it's fine. It's
But I can't hardly resist, so.
So with that same problem,
Uh-huh.
find the rate of change between 1 and x.
Okay. The function again was x squared plus 1. So the average rate of change between 1 and x. Remember what my formula was for average rate of change?
Yes.
What was it?
Well, which value would be b or a?
B is always the bigger value, the one to the right.
Okay. Oh, right, because it's saying
Always
between 1.
right. In other words, if it's between A and B, then B is the first one you put. And
Right.
the bottom has to be in the same order. As long as the bottom's in the same order, it doesn't really matter. I could do f of A minus f of B. As long as I did A minus B in the bottom, I'm going to get the same number.
Oh, okay.
Okay? So they said between 1 and x, right?
Yes.
All right. So it's f of x. Instead of b, it's x minus f of 1, all divided by x minus 1. And again, I don't know whether x is less than 1 or greater than 1, right?
Right.
So, in other words, when we had the b and the a, I knew b was bigger than a. Well, here I don't know. X can be anywhere along the x-axis. And so it doesn't matter because I went in the same direction. In other words, that's going to give me the same answer as f of 1 minus f of x over 1 minus x. These two things are the same. So
Okay.
it doesn't matter whether x is greater than or less than 1. And now to solve, so I'm going to work with the one on the left. What goes in for f of x?
X squared plus 1.
What's f of 1?
2.
So now I have x squared minus 1 in the numerator, x minus 1 in the denominator. Can I simplify that?
Yes.
Yeah.
Difference of perfect squares on the...
Perfect squares. So that's going to simplify to x plus 1. Not quite. They're not totally equal, even though I put an equal sign there. Now they're totally equal. In other words, this is equal to this. Because I added the domain restriction that does not go away just because I canceled this term out.
Okay.
Notice that x is perfectly okay for x to be 1. Then, that becomes 2 if x is 1. But it's not okay to divide by 0. And our original function, we were dividing by x minus 1. So you have to carry forth the domain restriction. So I would say that's your answer. If you put just x plus 1 without this, you might lose a point. Depends on your teacher, probably.
Okay.
Okay. The really big concept here is that I don't want to put numbers, I don't want to figure out the numbers and put it like that. I want to always make this f of b minus f of a, and then fill in my numbers afterwards.
Right.
Mainly because with calculus, you're always looking at these. In other words, you can have extremely complicated stuff in the parentheses. Okay? If I look at my original function, what is f of x plus h?
X plus h quantity squared plus 1.
Exactly. And that's the kind of stuff you're going to be doing in calculus a lot. Then you have to expand that.
Right. Like a FOIL?
Yeah, by just foiling it. Remember what we're always doing in calculus is f of x plus h minus f of x. So after I expand it, I'm still going to subtract out the original function. And all of that goes in the numerator. But the key part to understand is this part here. No matter how complicated that thing looks, or whether it's a number or a variable, does not matter. Its meaning is wherever you find x, you substitute that.
Okay.
Which is exactly what you did there.
Okay.
What else, William? It feels like we're doing some problems we've done before, but I might be getting you. I told my last student that also when he gave me the x squared minus 4 over x squared minus 9. I said, we've done this one. And he says, no, I don't think we have. And then I remembered that I have a couple of Ralston Valley pre-calc students. Might even have 3, I think. So you're all probably getting similar problems.
Yeah, it's probably the same review sheet.
It might be. He was trying to send it to me, and I couldn't get it sent to my email. But he was able to verbalize everything anyway.
So solve algebraically for x. 2 to the power of x plus 3 equals 6.
Solve algebraically?
Yes.
Meaning don't use your calculator?
Yes.
Okay. What's my first challenge here? Notice that there is no common exponential base between 2 and 6.
Right.
You can't do it that way. Be nice if that was an 8. And then I can just write it 2 cubed, right? And once I've written it 2 cubed, then 3 is equal to x plus 3. And then it's easy. But we have no commonality here. There's only one way to solve this. What is it?
Do we turn it into log form, or do we take the natural log of both
We
sides?
take the natural log of both sides. In other words, you have to utilize logs because we're looking at an exponential equation. And most exponential equations you can't solve algebraically. No way to do it. In fact, there's no way to do it without a calculator, really. Once I take the natural log of both sides, now that allows me to bring down the x plus 3, put it on the algebra line. Now it's an algebraic equation, and I can solve it. However, I guess I can just go ahead and divide both sides by natural log of 2. Gets rid of that number. And then I can subtract 3. So that gets rid of that number. So x is equal to that. And that's your answer. In other words, you don't need a calculator for your answer. You can give this as your answer. That's actually the best answer.
Right.
If you wanted a decimal approximation of this, you'd need a calculator.
And can you simplify the natural logs or the 6 or the 2?
No, you can't. For one thing, the rule is this. If I have ln of 6 minus ln of 2, that's the same thing as ln of 6 divided by 2. But notice that's not what we're looking at. We're looking at ln of 6 divided by ln of 2. So there's no simplifying that. If I have the ln of 6 over 2, then yeah, I could say, well, it's the same as the ln of 3, or it's the ln of 6 minus the ln of 2. But when I have log divided by log, can't simplify that any more than if I had natural log of 2 times the natural log of 6. No way to simplify that either.
Okay. Use Newton's law of cooling. A thermostat reading 72 degrees Fahrenheit is placed in a refrigerator where the temperature is a constant 38 degrees. If the thermometer reads 60 degrees after 2 minutes, what will it read after 7 minutes?
Okay, Newton's law of cooling. Do you have it memorized?
I do not. My teacher said she'd give us the formula on the test.
Okay. Is it times? I think it is times. It's times E. Is that right? Do you have access to it right now?
What?
Do you have access to Newton's law of cooling?
I can look it up real quick.
Can you? I can look it up too, but I'm not sure how quick it would be. Oh, hold it. I think I have it open to that page already. Excuse me. No, I don't. I was doing hyperbolas. Not that easy.
It's initial temperature, or temperature of the medium plus.
This a plus sign?
Yeah.
And this is correct, right? Is it e to the kt?
I think so.
Yeah, and or maybe e to the minus kt.
Right.
Maybe I should look it up. Because based on the logic of exponential decay.
Oh, the one other thing, it's the initial temperature minus the temperature of the medium.
Oh, I got it backwards?
Yeah, inside the
This
parentheses.
is O and this is M?
Yes.
Okay. Let's see, I'm pretty sure this is on page 600 exactly. I've looked it up before. Not so much for that. It wasn't on page 600. Hold on. Look it up in the index. Oh man, I hate these indexes. Oh, they already have indexed it. Newton's law of cooling, 307. That's close, huh? 600. Yeah, it is e to the minus kt.
Okay.
And yeah, you're right. It's t sub o minus t sub m. Yeah. Okay. There's got to be a reason why they insist upon putting that negative sign in there. It just does not seem to me like it's needed. Because
Yeah.
if I put the negative sign in there, I'm going to come up with a positive k. But if I didn't put the negative sign in there, I'd come up with the same number, only negative, I believe. So I don't quite see the purpose of the negative k, but that's not the reason why. So what do I fill in here?
38 degrees for T sub M.
Okay, what about t?
Oh, 60 degrees.
So I got 60 equals 38 plus, what goes in there?
72 minus 38.
Yeah, and there's one clue that the mistake I made, I would notice it immediately because I would end up with 38 minus 72. And I know that this has to be a positive number. Okay, so I would know I would have to reverse them. You understand what I'm saying?
Yes.
I guess it doesn't matter if she's going to give you the equation, but now they're telling me that that all happened in 2 minutes. So I'm putting in 2 for t. In other words, it went from 72 to 60 in 2 minutes. So the k that I'm going to calculate, notice k is the only thing left there that's a variable in this equation. The k I'm going to come up with is going to be based on a t that's in minutes. Then I'll be able to answer that once I figure out what k is. Okay. Well, that's 34. What do I do?
Subtract 38 from both sides, and you get 22 equals 34 times e to the negative 2k. And then divide 34 by both sides. Divide both sides by 34, and you get 11/17 equals e to the negative 2k. And then take the natural log of both sides, and you get natural log of 11 over 17 equals negative 2k. And then divide both sides by negative 2, and that's the exact answer for k.
Again, we're going to have a negative numerator and a negative denominator, so k comes out to be positive. Now, if I didn't have that negative, am I wrong here? If that negative sign, if I didn't use it, then I would end up with a negative k. Oh no, hold on. What would I end up with?
A positive k.
Well, no, hold on. I mean, if I didn't use it at all, And this would be 2k. Oh yeah, I would divide by positive 2 instead of a negative 2. Gives me the same k. The only difference between the 2 and the negative 2 is k will be the same number, only with a negative sign on it.
Right.
It doesn't seem to me like you have to use that in the general formula. I would be perfectly fine if I left it out.
Right.
Just end up with the same value for k, only it would be negative. And then when I write the specific formula, I'm going to have a negative in front of it. So I'm back to where they'd want you to be. And that's why it's always puzzled me as to why they want you to stick it in there in the first place.
Yeah, it seems problematic to put it in.
Well, I don't see any problems with using it. I just don't see any purpose. Other than to tell you that it's going down. In other words, whenever you have a negative up here, you know you either have exponential decay or you have Newton's law of cooling. You know it's not Newton's law of heating, right?
Right.
Interesting. I wonder if it applies. I wonder if Newton's law of heating actually applies. Let's say the medium is not 38 degrees, but 88 degrees. And let's say it doesn't go down to 60, it goes up to 75 in 2 minutes. Now, do you suppose this equation still applies? You'd end up with a negative here. In other words, t sub O minus t sub m is going to be a negative number. And you'd probably end up with a negative k instead of a positive k. And you'd be taking that to a positive exponent. I bet it would work. I bet you Newton's law of cooling applies whether you're cooling or heating. But I might be wrong. Seems like it should. The physics or the math, whatever you want to call it, shouldn't matter whether something's cooling down or heating up. You know, if the medium temperature that you move it into is hotter, I'd almost bet money that it works.
Yeah.
The only reason is, if it worked, why would they call it Newton's law of cooling? Why wouldn't they call it Newton's law of heat change?
Right.
Oh, and then once we have k, then just you have your specific formula and substitute 7 for t, and you'll get your answer as to what temperature it moves to after 7 minutes.
Right.
Most all of these questions you're giving me all have the same pattern. And that is, they give you, whether it's Newton's law of cooling or exponential decay or growth, whatever, they give you enough information to let you figure out what k is, or r, be it the case. And once you figure it out, then you have the specific equation for that particular model.
Right.
And then you can answer any question regarding varying times. In other words, what happens after 7 minutes? What does it go to? Well, in our problem, t would still be equal to all of that, only now up here we're going to put in a negative natural log of 11 over 17 divided by 2 times 7. And I know you and I did this problem because we kept getting the wrong answer and we couldn't figure out why. And it's because I had a hard time getting this thing defined properly on Wolfram alpha. In other words, it's not that easy to put that in there. Not that that's bad. I don't have any problem with going over some same problems. You're reviewing for the test, so you're just looking for the tough problems that you want to make sure you know how to do.
Right.
But again, that is just a number, all of that complex thing. There's no variables in there. Pi and E, people have a tendency of seeing variables. So if you stick one in an equation, they think, oh, there's a variable in there. But they're not variables. Constants. All right, what else you got? You got anything that's a 5-minute problem?
This one shouldn't take that long. I think I don't really have any big problems left.
Okay.
Find the equation of the hyperbola with the center at 1, 4, or with a center at 1, 4. Oh, no, sorry. Yeah, with the center at 1, 4.
Okay.
Focus at negative.
There's only one center.
Right, yeah.
There's 2 foci, but.
And 2 vertices.
Right.
And then 1 vertex at 0, 4.
Did they give us the foci?
Oh, sorry, yeah. One focus at negative 2, 4.
They just gave you one focus?
Yes.
Okay. So, very first thing I like to do on these is determine whether they're horizontal or vertical. Can't do much of anything because I don't know the general formula unless I know whether they're horizontal or vertical. So if I put the center right there and I say the focus is, if the center is at 1, 4 and you have a focus at -2, 4, that tells you immediately what kind of a hyperbola it is.
Right.
Is it horizontal or vertical?
Horizontal.
Yeah. In other words, I know that it's going to do something like that and something like that. And do I know the other vertex?
Negative 2, 4 is one of the foci.
Oh, not the vertex. Yeah.
Yeah. The one vertex it gives is at 0, 4.
Okay. Let me redraw this. 0, 4 is right there. Remember, that's the center. So the thing has to look like this. In other words, it's got to go through its vertex. And now do I know where the other vertex is? And the other foci,
yes,
for that matter. Where's the other
they're the same. 2, 4.
Yeah. Hardest thing about these hyperbolas is drawing them, having room to label all the points. And did they want the other foci? One of the key positions is the other foci. Although we don't really need it, what's the question? Is it to come up with the equation? Or is it to graph
it? Find the equation.
Well,
and graph, but.
Well, okay. If it's just to come up with the equation, we don't need to find the other foci. Because I know what C is. In other words, I need to solve for A and B, right? To come up with the equation?
Right.
Okay, because the general equation is this. X minus h squared over a squared because it's,
horizontal.
yeah. And the a always goes with the variable of the major transverse axis. And the major transverse axis is if I draw a line through all those points I have there. In other words, the line that connects the two vertexes, or you could say the two foci, that's the major transverse axis. And A is measured along there. So I know H and K, and I do know A. A is that distance right there. What's that distance?
1.
Okay, so let me write as much as I know. I know x minus 1 squared minus y minus 4 squared all over A is 1, so 1 squared. And the whole thing, I need a b. And the whole thing is equal to 1. And I need a space between that. There. So I know that much. So the only thing I still need is b. Well, the one thing I know from the information they gave me is c. What's the equation that relates c to a and b?
The Pythagorean theorem.
What is it?
C squared equals a squared plus b squared.
Okay, good. And I'm solving for b. What is c?
The distance from the center to both of the foci. So,
yeah, we never put we can go from this center to this foci. In other words, that's why I said that it isn't absolutely necessary to figure out the coordinates on this foci over here, because I can get my c from that distance.
Right.
What is c?
3. Plus or minus 3.
Yeah, in this case it would be minus, but I'm going to square it anyway, so it's not going to affect my b. Okay, so I'm going to take negative 3 squared and make it 9, or positive 3, either one. Still comes out to be 9. That is equal to 1 plus b squared. B squared equals 8. B equals square root of 8.
2 root 2, right?
Yeah. Actually, the only thing I really need is b squared, right?
Oh, right, yeah.
I didn't actually need to solve for b. I needed b squared. And that's a good thing, because notice that when I solve for b, I get a plus or minus root 8.
Right.
Well, that's not that hard to believe, because notice that box, b, is the measurement from there to there, but it's also the measurement from there to there. So the plus or minus makes sense. But I didn't have to worry about it because I only need b squared, not b. And so I'm going to replace my b squared with 8, and there's my answer. And even if they ask you to graph it, do they automatically want you to label all key points?
I'm not sure. I don't think I have on past tests, and she hasn't marked me off.
Okay. So. There probably is one last question they want on this. The equation of the asymptotes.
Yes.
Okay, there's a general form for that. If she gives it to you, good. Oh yeah, it was on your sheet that you sent me.
Yeah.
But I've remembered it now. It's a straight line, so I know it's going to be y equals plus or minus. If it's this kind of hyperbola, is it b over a or a over b?
B over a times x.
And then it's times x minus h, the center,
right,
plus k. which means in this case it's plus or minus. Well, now I do need to, that was 2 root 2 over 1. X minus 1 plus 4. There's the equation of your two asymptotes.
Right.
And remember that they should look like y equal mx plus b.
Right, straight line.
In other words, there's no squared here, because that would be the equation of a hyperbola. And you don't have to memorize that. She's going to give you that. So.
Right.
All right. William, you have one more scheduled tomorrow? I think you, yes, no?
For 5:30.
Okay. I will see you. Let me just verify if that's what my calendar says. Yeah. I will talk to you at 5:30 tomorrow.
Okay, great. Thank you very much, Mr. Cowan.
You're welcome. Bye-bye.
Have a good night.
You too.